again, guys. We're always here. Okay, first, let's share the overleaf with Nagin. And priorities. How many emails? 130. Found it. This is it. But honestly, guys, I want to thank you again for being here. If you were not here, I wouldn't study. So, overleaf, yeah. Let's go! Woo! Then whole set ranking. Then I want to share. Hit the share. One step after another. Woo! Let's invite. So that's it. Perfect. Woo! One step ahead. Let's open ChatGPT. Now it's time for ChatGPT because we want to go to LDA. We want to go behind its math. Now reading LDA is so easy. We went over all the parameters, all the definitions. Now we are ready for the elbow evident lower bound. BO. So I'm bringing up here, and then I'm going to ChatGPT, ranking algorithms, and the mathematics of LDA. And then we learned about mixture of unigrams. That sounds close, that can be something, but we implemented in the code and it didn't work, and we said, yo, we need to implement the effect of ranking anyways. Maybe that works and is good enough, we don't need it. But yesterday we had a talk and we said, even if you find that the effect of ranking and LDA and other things are working well, this is not our main question. This is just the starting point. We want to add features, we want to add the effect of ranking, because these different customers that come and see these click sessions, they are not observing only one list, ordered list, they are seeing different orders list, personalized, and then it is the art of finding the effect of the ranking. So they had this beta and theta were decoupled, couldn't decouple them, then they started to estimate evident lower bounded. And next step, we open ChatGPT. Now let's go to the old, and we can latent Dirichlet allocation. And let me share it with you guys. Jeez, alright. Alright, variational inference. That was the part we were reading. Jensen inequality. The likelihood is complicated, intractable. We find the tightest lower bound. Instead of maximizing the lower likelihood, we maximize the tightest lower bound. One considers a family of lower bounds indexed by a set of variational parameters. The variational parameter by an optimization procedure attempts to find the tightest possible lower bound. Well, the ideal family of lower bounds is to consider simple modifications of the original graphical model in which it was on the left, And we learned about graphical models yesterday. Edges and nodes are removed. Consider in particular the LDA model in figure 5 left the problematic coupling between theta and beta. Let's take a look. How do they talk about coupling? I hate optimization. 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 I wanna open a new window. How did we do that? New window. Cascade. What is cascade? Guys, I have headache, a bad headache. I don't know why. You know, I woke up in the morning and started eating olive. That's beautiful graph actually. All right, that may explain what's happening there. Let's go figure 5. Let's see how they decouple. So this is it. Beta and theta are coupled. So this way is decoupling beta and theta. Actually, in the second one, theta and z are kind of independent. That's very weird. Because theta should say how we generate z's. But here it says no. And there is no w, by the way, in the left hand side. We have gamma, we have alpha. Perfect. All right. Body coupling between theta and beta. By the way, how theta and beta are coupled? So beta comes here, theta comes here. But I think that was just in the formula. Arises due to the edges between theta and z and w. Where is w? Oh, z is w is after z. By dropping these edges and the w nodes, why should we drop w? And okay, what we want to find is alpha and beta. So we don't care about what w is what we are observing. That's the thing though. And endowing, let's check endow. Endow or endow? I say endow. Endow. Endowing. So we are endowing the resulting simplified graphical model with free variational parameters. We obtain a family of distributions on the latent variables. This family is characterized by the following variational distribution. Let me write, let me open, let me rank, let me variational. Alright, Q of theta and z equal, by the way, this is not our main focus. I'm just doing it as a side task. So main focus from now on is, like as I said, featureizing, dynamic ranking. This is just we want to see if we get anything here or not. This is not the main focus anymore, to be honest. Q of theta z given gamma and phi equals Q of theta given gamma. La 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 la. What kind of behavior is that in front of camera? Suddenly la 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 la. Wait, why doesn't it open up? Open up. Yeah, what happened? Not me, man. Smart view. Yeah. No, no, no. Oh, oh, oh. Oh, you cannot see it anyways, so fuck it. Okay, now we have this divergence. Information divergence. Q of theta and z given gamma and phi equals q of theta given gamma pi. N is the number of words. N1 to N. What kind of Q? Well, why do you use the same notation? Q of theta given gamma, Q of z given phi. Z and phi. Let's see what is... Alright, what is phi, what is gamma, what is z? Zn we know, what is phi n? Parameters gamma. Okay, gamma is similar to alpha. Alpha was the generative one, gamma is the predictive one. And the multinomial parameters phi 1 to phi n are the free variational parameters. What are they? Free variational parameters. So this is Dirichlet parameter, and these are free variational parameters. Gamma. Shout out to all the Greeks because of their contribution to humanity. All the math depends on them. Thanks for gamma, thanks for phi, but I fucking hate XC. Remove that shit. I don't like that. Alright. And there is another one, zeta. Zeta and XC, disgusting variables. I'm not getting involved in any kind of research that includes XC and zeta. Gamma, alpha, phi, small, big phi, psi is fantastic. What else? Kappa is nice. Kappa or kappa? And omega, good stuff. Lambda is eta is nice. Eta is beautiful. Chi squared, good stuff. Good shit. Are the free variational parameters. Alright, having specified the simplified family of probability distribution, the next step is to set up an optimization problem that determines the value. Alright, this is the replaced one, but what is the real one that we had? This is the formula, probability of, we wanted to, what is our main likelihood, right? We are observing these words, right? And what are our parameters? Alpha and beta, right? That's the thing. We want to always maximize the likelihood. And what is likelihood is what we are observing given our parameters. What we are observing are the documents. Our parameters are alpha and beta topics and their multinomial parameter. Yes, we added some structure in between words and how they are generated based on these topics that we can actually, there is like a mid step here. We have probability of words and their assignments, and then given theta and beta, alpha and beta. But from this we can compute the probability of W given alpha and beta, right? So perfect. So what we have is probability of W given alpha and beta is probability of theta and Z and W given alpha and beta over probability of theta and Z given W. That's interesting. Yes, okay, that's just base rule. And alpha and beta. Then we can compute this. We will have this formula gamma of sigma alpha I. Let me fix my house. Over pi of gamma I, gamma of alpha I, integral. That's the formula we will have by I 1 to k number of topics theta I alpha I minus 1, and then we have number of the words, number of the topics, number of the vocabularies, so with probability I theta I, it's from topic I, and from beta I topic I, not Zi, right? Yeah, we generate vocabulary J, and okay, it has to the power of Wn to the J. What does that mean? What does that Wn to the J? Okay, I think Wn to the J means if Wn, word n, in the vocabulary, no, it should be either 0 or 1, right? Each word in the, what is n? N is the number of documents we have, right? So we are multiplying the probability of each document, they are independent. Each document, how do you generate the, no, actually n is not that. How many documents we have? M documents. So it's just probability, okay, it's probability of one document given alpha and beta. It's not the whole probability of corpus. So Okay, so probability of one document, we want to see, first of all, how do we do it? Each word in the document that we are observing, wn, n1 to n is the n1 to n is the number of words in our document, right? And each one of them, if wn exists, so wnj should be the j that gives us the count of wn in the vocabulary ordered list of all the vocabularies. I think that's wnj. Yeah, and if the word doesn't exist in the document, we don't go over it actually. So wn of j is, what is it? It should be better. Like it should be, we have a counter to the wn. Fuck that! From vocabulary, from set of vocabulary to the set of 1 to n. So wnj is just the index of that motherfucker. And when you say beta I j, j means the counter of that wn. And theta I, with probably theta. Why do we approach for I? Why do we train to line? Because the other theta I are the probability of having one multinomial, right? We are going over all. At the end we have d theta, which makes sense. So we are going over all the multinomials in the Dirichlet family generated by alpha. And now that, let's assume we chose our multinomial, now probability of picking that topic is theta I. And beta ij makes sense. We have first multiplication of all the words because of the exchangeability, because of the independence, and we can have from different topics. Why do we have? So words are independent. Yes, words are independent. I think this last pi, that is j1 to v, is quite extra. Yeah, I think probably explains more a function which is intractable to the of theta and beta. But this form was so random, sudden. It is so sudden. Like it, we need to unfold it and open it up because suddenly they propose this. They propose this. What is it called? Graphical model, and then they propose this formula, which is decoupled, but I don't get. Like every step, intuition behind it is hidden for me right now. Was this on a move? Okay. Where does it come from? I'm like, where is it coming from? Alright, let's go chat GPT. So let's ask this. Mm-hmm. Exactly. So it's just a counter. Having a simplified family of properties during the next step is to settle an optimization problem that determines the value of variational parameter gamma and phi. Ah, dude, I feel this. My brain is crushed. Brain is crushed. I love that. Actually, ChatGPT kill all the magic. So it's a classic move in variational inference. That's good to know. It's something standard. It's not like genius move. It's standard, classic. Classic variation, especially in the context of mean field approximation. Let's walk through the intuition and justification for it step by step. In the original LDA model, we want to compute the posterior property of theta and z given omega, alpha, and beta. Not really. Is intractable to compute exactly because of the coupling between theta and z. So we need to approximate q of theta and z is p of theta and z given omega. Why do we need, actually I don't get it why we need. Infill assumption and q. Between latent variable. What are our latent variable here? It's theta and beta. Beta and theta are latent, but they were coupled. So we want to have latent variables that do not cause coupling. Theta for gamma, z for phi, and the zn. Theta and the zn and zn from each other. So the new graphical model. So it's a balance. It's between simplicity and flexibility. Natural families assume. Computational approximate percent factors. Q of theta given gamma is another Dirichlet, same family as probability of theta. Zn given is a categorical, same as probability of Zn given theta. Okay, that sounds good. We don't want words because words, we are dealing with the latent ones. It says, what are the latent ones? Theta and Z, right? And but in our real model, the theta depends on alpha. So we need to have the posterior to compute our likelihood, huh? That's why. Probability of theta and Z given. Wow, it copy pastes the formula so good. You need to compute the posterior theta and Z. This integral has not have a closed form. Probability of double W given Zn. Okay, does not have a closed form, so taking derivative of it is difficult. Intractable. Why we need a posterior property of okay, let's go forward. Okay, simplified family of probability distribution. The next step is to set up an optimization problem that determines the value of the variational parameters gamma and phi. So we want to find now we don't want to find alpha beta, we want to find gamma. Makes sense. As we show in appendix A, decide what is it? Desideratum of finding a tighter lower bound on the log likelihood translates directly to the following optimization. Well, that's interesting. I don't get that part. I think that's the intuition. That's the mathematics. Desideratum desideratum. I say desideratum. Desideratum. Something that is needed or wanted. Desideratum. Requirement. Okay. The desideratum of finding a tight lower bound on the log line translates directly to the following optimization problem. It is the one that minimizes the divergence between probability of theta and z given omega alpha beta, which is the posterior. Oh, so we are just finding the posterior. We are not, look, what are our latent variables? Alpha and beta. Yeah, I didn't get why this is an option still, right? I read the answer from ChatGPT. I didn't get it. And q of theta and z, instead they come with another variable that says q of theta and z, remove w, alpha and beta, we say gamma and phi. Argmin of that. I didn't get that. The optimizing values of the variational are found by minimizing the Kullback-Leibler divergence between the variational and the true oscillator. This minimization, this is about information theory stuff. Minimization can be achieved via an iterative fixed point method. Isn't it iterative fixed point method? Is it EM? I didn't get this part. Let's look at it. Okay. So, can you explain why we use the KL divergence and also why we want to estimate probability of theta and z and w alpha and beta. And not estimating the likelihood probability of W given Okay, our true goal is to maximize the likelihood log probability of W given alpha beta, but we can't compute this exactly because it involves integrating over interactable latent variables. D theta dz, alright, that's interesting. So instead, which by itself the formula for it is probability of theta z w so this formula first of all is wrong. Probability of W given alpha beta is ZW, but we are not even using this motherfucker inside the integral. We are using um, theta z given W, then probability of okay, so instead we aim to optimize the lower bound, the evidence variational inference. Alright, take me to the world of elbow and let's unpack it. Variational trick. We introduce a simpler distribution Q of theta z to through posterior derivative of theta z given W. And then we write log of P is loss over gamma and phi. This is the variational trick, alright? Expected Q of log of P theta z. Okay, that's about the expected of Q is about formula for KL divergence. Log of P minus log of Q. That's the formula for the DKL divergence, right? It is log of P minus log of Q expected regardless with regard to Q. What is the formula for DKL? Alright. Oh, so it's not exactly that shit there. Minimizing KL, log of PW is fixed. So once you minimize KL, it means you maximize elbow. But what is DKL, by the way? I still didn't get it. Okay, yeah, maybe I got it. By the way, why do you remove alpha and beta sometimes? I hate that. We want to maximize this. We want to maximize. Wait, what? Why is this true? I don't get it. Why? log q minus log p. Isn't it the same shit here? The sum of these two, log of q minus log of p. Oh, these are two different. It's log of q minus log of, so it will be expected q of log of p of theta z, comma w, or minus log of p theta and z given w. When we divide them, double, it will be p of w. Right, that's right. But p of w is not constant. Log of pw is constant with respect to q. It's independent of q. Yes, now it makes sense. Okay. Yes. What is this value? KL divergence, log of PW is on the top. So this is a technique in variational inference. Observed data is x, latent variable is z, and we want to find the latent ones. Model joint probability of x and z. So we have observed and we have latent x and z. Your goal is to do Bayesian inference probability of the latent given the observed. what is the unit P of X? This is intractable. Here our Z is what is it? Is Z and theta. Our observed is W. This is intractable because the marginal likelihood P of X is P of X and Z. dz is intractable. It's often impossible to compute exactly. Additional inference, so we introduce a tractable family of distribution Q of Z and lambda to make Q like P of Z and X. So by the way, divergence is a metric for closeness. Why should we use KL as the metric for closeness of two variational inference. No elbows. In variational inference, you are trying to approximate a complex posterior distributed area. Need to avoid this divergence measure function that compares to distribution. Why KL is specifically the equivalent? Why not a metric? Non-negativity. Distance. Okay. What are fees instead of? So what is the equivalent of fee in our formula? Zn given phi n. I think the next paragraph will talk about it, but okay. So each phi n is a problem. It's actually a theta. That's crazy. Is That's crazy, right? Because we fix our theta once we fix it. Maybe the average of them will be theta. Gamma is kind of similar to alpha. Phi n is okay. So if phi n is distribution over those over topics, it's like saying, all right, I have theta. I don't wanna have distribution over topics all connected to one theta. I am separating them with phi n. Now they are totally independent, and they are totally independent and convert to data. Data was distribution over the topics, nothing. My soft guess posterior belief about which topic generate word W in this document. Exactly. Now they have more room because they're independent. Kyozani is the problem. Okay, so we don't honestly want to find a really tractable, right now at least, optimization algorithm for our EM method. It works fine. So this is the formula for stars. VNI star is IWN exp of expectation of Q log of W. That's a scary formula. And gamma I is alpha I plus N1 to N VNI. The expectation, as we show in Appendix A, the expectation in the multinomial update can be computed as follows. Where psi is the first derivative of the log gamma function, which is a computable via Taylor approximation. Ooh, there are so many things involved here. Equation 6 and 7 have an appealing intuitive interpretation. The dirichlet is a posterior dirichlet plus some terms. It's akin to using Bayes' theorem. For fixed elements. So this is their algorithm, 1 over k, uniform. And repeat for n1 to n, for I1 to k, and phi ni t plus 1. This is the way you update it. And this is a study that you can reproduce, motherfuckers. You cannot write papers that people cannot reproduce. Then don't call it paper, call it a teaser or something, some marketing strategy to that you wanna say, okay, we worked on this stuff. If you want a new person, you wanna work with us, come join. Pseudocode. By the way, one thing we are studying LDA is like finding a better way, or see if we can trick LDA to find our clusters in a ranking case. Well, LDA obviously did not work well. Our EM is doing better. It takes more time. LDA is like established, so we may say, all right, if we can change LDA to find those clusters, it's good. But this is not the main part of us. Part of our work. We want to add more things to it. So this is, I told you, I just keep reminding myself. Now that I read more, it seems we are not, actually these are not the things I like, and they are not the main point of our research. K-fold. Good, but reading LDA was a relief. You don't need to maximize likelihood. There are other things you can try to approximate, and I love approximation, and I hate optimization. That's the interesting part, smoothing. Um, we were talking about capping the weights, and what was that in our meeting? Stabilizing weights. I think that's related to it. It's not exactly it, but it's all about the zeros that show up. This paper, we want to look at it too, actually. What was the beta? Beta is 1 to K, Z is 1 to M. What was M? Number of documents? Yes. Alright, now I wanna go faster mode on this stuff because where is my X?
Journal of Machine Learning. Six example. In this section, we provide an illustrative example of the use of an LDA model on real data. Our data are 16,000 documents from a subset of the TRECAP corpus, Harman, 1992. After removing a standard list of stop words, we used the M algorithm described in section 5.3 to find the Dirichlet and conditional multinomial parameters for a 100-topic LDA model. The top words from some of the resulting multinomial distributions P, WZ, are illustrated in figure 8, top. As we have hoped, these distributions seem to capture some of the underlying topics in the corpus, and we have named them according to these topics. As we emphasized in section 4, one of the advantages of LDA over related latent variable models is that it provides well-defined inference procedures for previously unseen documents. Indeed, we can illustrate how LDA works by performing
Okay,
inference on a held-out
LDA.
document and examining the resulting variational posterior parameters. Figure 8, bottom, is a document from the TRECAP corpus which was not used for parameter estimation. Using the algorithm in section 5.1, we computed the variational posterior Dirichlet parameters gamma for the article and
What was that? Muscles going away. Apathy. No. Just what was it? Atrophy. Okay, atrophy. All right.
variational posterior multinomial parameters phi n for each word in the article. Recall that the ith posterior Dirichlet parameter gamma I is approximately the ith prior Dirichlet parameter alpha I plus the expected number of words which were generated by the ith topic, CEQ7. Therefore, the prior Dirichlet parameters subtracted from the posterior Dirichlet parameters indicate the expected number of words which were allocated to each topic for a particular document. For the example article in Figure 8, bottom, most of the gamma I are close to alpha I. 4 topics, however, are significantly larger. By this, we mean gamma I alpha I greater than or equal to 1. Looking at the corresponding distributions over words identifies the topics which mix to form this document, Figure 8, top 1007 Blay, Angie, and Jordan. Further insight comes from examining the phi n parameters. These distributions approximate p, z and w, and tend to peak towards one of the k possible topic values. In the article text in Figure 8, the words are color-coded according to these values, i.e., the ith color is used if qn, zn equals 1, 0.9. With this illustration, one can identify how the different topics mixed in the document text. While demonstrating the power of LDA, the posterior analysis also highlights some of its limitations. In particular, the bag of words assumption allows words that should be generated by the same topic, example William Randolph Hearst Foundation, to be allocated to several different topics.
By the way,
Overcoming
it's
this
very
limitation
interesting.
would require some form of extension of the basic LDA model. In particular, we might relax the bag of words assumption by assuming partial exchangeability or Markovianity of word sequences. 7 applications and empirical results.
Like, by the way, LDA, they use it for topic model. It's okay, topic modeling, yeah, of course, but grammar, honestly, does not matter that much in the meaning of a sentence. Sometimes it matters, but I wanted to say in the natural text, we have an order based on grammar, which LDA ignores it, but come on, it's not that big of a deal. Alright, right? However, in ranking, order matters. That's the whole shit. Okay. I do it in a bit. Why did I say it? I send it, I do it in a bit. Alright, application.
In this section, we discuss our empirical evaluation of LDA in several problem domains: document modeling, document classification, and collaborative filtering. In all of the mixture models, the expected complete log likelihood of the data has local maxima at the points where all or some of the mixture components are equal to each other. To avoid these local maxima, it is important to initialize the M algorithm appropriately. In our experiments, we initialize M by seeding each conditional multinomial distribution with 5 documents, reducing their effective total length to 2 words, and smoothing across the whole vocabulary. This is essentially an approximation. We trained a number of latent variable models, including LDA, on 2 text corpora to compare the generalization performance of these models. The documents in the corpora are treated as unlabeled, thus, our goal is density estimation. We wish to achieve high likelihood on a held-out test set. In particular, we computed the perplexity of a held-out test set to evaluate the models. The perplexity, used by convention in language modeling, is monotonically decreasing in the likelihood of the test data, and is algebraically equivalent to the inverse of the geometric mean per word likelihood. A lower perplexity score indicates better generalization performance. Point 3. More formally, for a test set of M documents, the perplexity is perplexity, test, equals exp sigma md equals 1 log p, wd, sigma md equals 1 nd. In our experiments, we used a corpus of scientific abstracts from the C. elegans community, Avery, 2002, containing 5,225 abstracts with 28,414 unique terms, and a subset of the TRECAP corpus containing 16,333 newswire articles with 23,075 unique terms. In both cases, we held out 10% of the data for test purposes and trained the models on the remaining 90%. In pre-processing the data, 3. Note that we simply use perplexity as a figure of merit for comparing models. The models that we compare are all unigram, bag of words, models, which, as we have discussed in the introduction, are of interest.
Example, by the way, the William Randolph Hearst Foundation will give $1 billion to Lincoln Center, Metropolitan Opera, New York. Okay, well, I want to see them. So we have arts, we have children, we have budgets, and we have education. Arts are new: film, show, music, movie, play, musical, best actor, first, York. Well, the labels for arts, they are chosen later. York, opera, theater, actress, love. Budgets, we have million, we have tax, we have program, we have budget, billion, right? Like you might say, how is budget related to state? Plan, money, programs, government. We have children, women, people. Like women, why should they be under the title of children? Years, families, work, parents, says. Like all these random words also need to be assigned to one family group. Topic: welfare, man, perfect, care, and life. Person care. Education, we have school, students, schools. School and schools are different. Education, teachers, high school, you mean. Public, teacher, and teachers are different. Bennett, Manicat, Namfi. These are just bullshit, I don't. What about center? Center was art. Center, I saw center. What are the black words? Number of topics. When number of topics increases, we want bigger perplexity, right? LDA, lower perplexity. So what is the perplexity? What is perplexity? Yo, what is perplexity?
Perplexity is a metric commonly used in language models and probability distributions to indicate how well a model predicts a sample. In the context of language models, a lower perplexity means the model is better at predicting the next word in a sequence. Essentially, it reflects how confused or uncertain the model is. The lower the perplexity, the more confident and accurate the model is in its predictions.
It's funny that LDA and stuff are talking about words, but they use perplexity as a metric, which is about the next word. Okay, there are two different corporas, and LDA does better. I think it is the first paper I am reading fully.
We removed a standard list of 50 stop words from each corpus. From the AP data, we further removed words that occurred only once. We compared LDA with the unigram, mixture of unigrams, and PLSI models described in section 4. We trained all the hidden variable models using M with exactly the same stopping criteria, that the average change in expected log likelihood is less than 0.001%. Both the PLSI model and the mixture of unigrams suffer from serious overfitting issues, though for different reasons. This phenomenon is illustrated in Table 1. In the mixture of unigrams model, overfitting is a result of peak posteriors in the training set, a phenomenon familiar in the supervised setting, where this model is known as the naive Bayes model, Rennie, 2001. This leads to a nearly deterministic clustering of the training documents, in the E step, which is used to determine the word probabilities in each mixture component, in the M step. A previously unseen document may best fit one of the resulting mixture components, but will probably contain at least one word which did not occur in the training documents that were assigned to that component. Such words will have a very small probability, which causes the perplexity of the new document to explode. As K increases, the documents of the training corpus are partitioned into finer collections and thus induce more words with small probabilities. In the mixture of unigrams, we can alleviate overfitting through the variational Bayesian smoothing scheme presented in section 5.4. This ensures that all words will have some probability under every mixture component. In the PLSI case, the hard clustering problem is alleviated by the fact that each document is allowed to exhibit a different proportion of topics. However, PLSI only refers to the training documents, and a different overfitting problem arises that is due to the dimensionality of the P-ZD parameter. Essentially, we are integrating over the empirical distribution on the topic simplex. See figure 4.
I need to get back to the gym.
This method of inference,
like I started wrestling and then the schedule conflicts, so I lost some workout sessions. And then my mom was here. When she was here, I was not doing anything, and then wrestling started. Now I go twice a week. Sometimes I used to go 4 times a week. And I'm finding the balance, the schedule that works with my time. So I am losing some stuff, but I need to hit the gym.
The model to overfit. The document-specific topic distribution has some components which are close to 0 for those topics that do not appear in the document. Thus, certain words will have very small probability in the estimates of 1011 Blay, Angie, and Jordan. Each mixture component. When determining the probability of a new document through marginalization, only those training documents which exhibit a similar proportion of topics will contribute to the likelihood. For a given training document's topic proportions, any word which has small probability in all the constituent topics will cause the perplexity to explode. As K gets larger, the chance that a training document will exhibit topics that cover all the words in the new document decreases, and thus the perplexity grows. Note that PLSI does not overfit as quickly, with respect to K, as the mixture of unigrams. This overfitting problem essentially stems from the restriction that each future document exhibit the same topic proportions as were seen in one or more of the training documents. Given this constraint, we are not free to choose the most likely proportions of topics for the new document. An alternative approach is the folding-in heuristic suggested by Hoffman, 1999, where one ignores the P, ZD, parameters and refits P, ZD nug. Note that this gives the PLSI model an unfair advantage by allowing it to refit K1 parameters to the test data. LDA suffers from neither of these problems. As in PLSI, each document can exhibit a different proportion of underlying topics. However, LDA can easily assign probability to a new document. No heuristics are needed for a new document to be endowed with a different set of topic proportions than were associated with documents in the training corpus. In the text classification problem, we wish to classify a document into two or more mutually exclusive classes. As in any classification problem, we may wish to consider generative approaches or discriminative approaches. In particular, by using one LDA module for each class, we have described latent Dirichlet allocation, a flexible generative probabilistic model for collections of discrete data.
Alright,
LDA is
bullshit. Shut up. Shut up. Alright, done with LDA. So the idea is that you can approximate and stuff. That's good. Perfect. Okay. Let's play some counter. One round and a half. You have lag. How is that possible? Oh, real noob is back. Oh, real noob is right number 4 or 5. Can I make it? That was unexpected. That's fine. Oof. Killed him through his shoulder. I didn't. Wow, it didn't hit. That's so fun. That's so fun. I like it. Dude, move. You should move. Honestly. The difference between me and a pro is that they move. So you should not stand still. You are good. See? You move, you are good. You're safe. See? You move, you are good. Ooh, 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 ooh. See? You are good. You are good. See? You move, you are good. Wait, how did he stood there? How did he stand? You move, you are good. You move, you are good. You move, you are good. Again, what case? That's not good for my image. That's not good for my image. That's not good for my image. Dude, this is just a mind game. They wanna bot kill you all the time, so you think a bot kills you. Just make it personal. They wanna make it personal. What the fuck you mean? Jesus, Jesus, Jesus. Why? Come on! Dude. Dude, I killed him though! They're so in front of us. Did you see that? But we need to fucking back kill them. Hey, John, fly. Let's go here. I think the battle is here. They're jumping over. Let them do it. Oh, actually, I was thinking. Oh, there was only 3 of us. Last time. One and 3. They always have 1 and 3 playing each other. When one wins, right? So we have 1, 2, 3, 4. Winners play with each other, losers play with each other, right? So let's say 1 and 4 are playing, 1 goes, 2 and 3, 1 and 2 should play with each other. And 1 and 2 should play together, 3 and 4, then 1 and 3, then 1 and 2, 1 and 3, 1 and 2, 1 and 3, 1 and 2, 1 and 3. 1 never plays with 4, right? I think that's it. It's always this. Oh shit. Why don't I headshot more? How are they so good? Jesus. Oh, man. Bot was better than me. Alright. We finished LDA. Next time I'm gonna quit my job. No, next time I want to. I cannot think. Should we do dynamic ranking and featureization? Or add a small decay factor in beta. Let's stay with LDA. Let's finish LDA and add the decay factor. Let's see if we can add the decay factor in LDA, and then we go for the featureization. LDA slash mixture of unigram. Or actually, we can go read the mixture of unigram paper. I'm not gonna read the mixture of unigram paper. Let's go this mixture of unigram code. Alright, stop guys, stop.